Okay, so good morning, everybody. So we first finished the reinforcement learning. So I'll be using the slides that are now shared. And after we're done with this, we will basically, I'll walk you again through our website. We make a sort of, recap of what will be on the midterm exam next week. And I'll give you some tips what you can expect. Okay, so reinforcement learning 2, there was as usual the lecture from UC Berkeley, which I think was very good. So I will not re-explain what has been already covered there, but I'll of course go through again our slides, and I give you a chance to basically to make it more interactive. And if you already have questions about the Berkeley lecture, you can already post them. Otherwise, we go through the topics and then we discuss as we go. Okay, so just the schematics. This is from the Sutton and Bartow book on reinforcement learning, which is freely available. At the end of the lecture, I will also show you the table of contents and show you where the topics we're covering are in that book. And I think it's a very nice textbook, in particular on reinforcement learning, but there's also this value iteration, policy iteration. So this is just the schematics, what is going on. So there is an agent, can take actions in the world, and from the environment, it receives back the next state and the reward. It's in a state, it does an action, next state, reward, and that's the cycle. And it's trying to figure out what to do, what action to choose, such that it maximizes this sum of expected future rewards that it keeps getting. And so that's it. Today, so most of the time we were confined to this grid world for basically all of the problems we were choosing. Today we will also show you some examples from robotics, from the real world, because we will also do basically this approximative reinforcement learning where you cannot afford to have a table with all these states. And you have to do it in a different way. So there will be this motivation. This is from the group of Tomáš Svoboda, where there is this tracked robot. It's a rescue robot, or it's called also USAR, Unmanned Search and Rescue. So they are participating in this DARPA Subterranean Challenge, and they had projects with firefighters. And so the problem is basically traverse difficult terrain and then perceive things as you go. And how to traverse this difficult terrain will be this example that we will look at throughout this lecture. So we will look at what the states are, how to design rewards, how to perform training episodes, and if there is also a simulator of this robot, which is often used, but there is always this reality gap, right? So something you learn in a simulator cannot be transferred one-to-one into reality. So for the motivation, it has these we call them flippers. So it's a tracked robot. It has these tracks, and then such that it can traverse obstacles, stairs. It has these flippers that have these additional motors that can, rotate the flipper around. It can change the configuration. And so that's an important control parameter, what the angle of these flippers should be. If there is an obstacle in front of you, or if there is a hole, like a pit in front of you, and that's what you need to control. So 2 main tracks, 4 sub-tracks, right. And then there's a rich sensor suite. There is a laser rangefinder, which is this thing. So it's sending arrays of laser rays in one plane, but such that it can cover more than one plane. It has this additional motor that it's rotating, such that it can sample more than one plane. And it has a omnidirectional camera. It has an inertial measurement unit, and and all this, this is the perception of the robot, and this is actually what is going to compose the state the robot is in. So we will see it in detail. And the control inputs can be the velocity vector, like for all the tracks, the flipper angle, flipper stiffness. We will see that again shortly. So the state may concatenate the proprioceptive measurements, which is something the robot itself can measure. So it's its internal state, so to speak. Roll pitch, it's basically how it's inclined, which can be acquired from the accelerometers, and then torques in the motors, velocity, obviously acceleration. And then there will be these exteroceptive measurements from the camera or from the laser rangefinder. So in particular from the laser rangefinder, the main benefit of these sensors is that you can really get an so-called elevation map of the environment. So basically, you see obstacles in front of you, and it's more, let's say, reliable data than if you were to extract it from a camera image. And it has a resolution of so you basically see the squares here. There will be 10 on this side and 30 on this side. And that could be one possible way of discretizing the information, or you can come up with some features. For example, that if this is lower than this, that this would be an obstacle. If it's the other way around, it would be like a pit, and that of course changes how you should control the robot. So so that's for the motivation. For the real world problem. And now, same for the action space. You always have to keep in mind that even if, let's say, the sensor space and the action space are continuous, eventually you have to discretize them with some resolution, and the higher the resolution is going to be, the harder, the bigger the state space will be, and the harder it will be to learn. So that's why, for example, the flipper angles, that would be also a continuous space, like four dimensions. But that will be a huge space. So instead, what you can come up with would be some kind of motor primitives. So some discretized configurations, like what you see here, right? So if you want to go up a stair, this might be a good configuration. This one is a configuration that maximizes observability, such that the sensors can see well that the flippers are not in the way. And this green versus red is you can set the motors into a compliant mode. That means that they are compliant. If there is resistance, they would sort of give away to that resistance. So they will behave softly, which could be good, for example, for smooth climbing down. So you can discretize the action space in such a manner, for example. Okay, and then comes the reward. So we've seen the rewards in, for example, in the adversarial search in games. There was usually like a 1 or 0 at the end if you win the game or not. Same goes for, you may have seen examples of artificial intelligence playing Atari games. So there is a lot of attention to reinforcement learning these days. There is also the famous AlphaGo Zero, which is the program that managed to learn chess and Go and one more game basically from scratch, just by playing against itself. And so in all these cases, the reward will be only at the very end. But the reason that you can afford it is because it's just an abstract game in simulation where you can basically play against, the agent is playing against each other for many times and in parallel, and you can learn in this way, which is, however, not the case for a real robot, because you just don't have the resources, the capacity, and also you will just break the robot. It just cannot go physically through thousands and millions of learning trials. So either you use the simulation and then you have to make sure you somehow bridge the reality gap, or you basically incorporate some of your knowledge and you design the rewards such that it doesn't only come at the end when it traverses the whole so imagine it goes through, I don't know, a disaster site, and then after half an hour the firefighter tells him, okay, this was good. And imagine that this would be extremely hard to learn. So so an alternative is that you design the reward such that some reward is available basically in every state, such as safe pitch and roll, avoiding tipping over, smoothness. It's better if you drive faster. And and then there could also be a way for the user, let's say this firefighter that is possibly teleoperating the robot to provide rewards. Okay, so yeah, that's for the sort of real-world motivation. We will come back to the robot also again during the lecture. This is an overview. We're going from these offline Markov decision processes to online reinforcement learning. This I don't have to repeat. We have done a lot of MDPs, and now we're facing an online problem where the transition probabilities and the reward are not known. Instead, we basically have to experience them as the as the agent acts in the world. So a transition that bridges the MDP world with reinforcement learning is that you do not have those transitions and the reward function, but you try to infer them as you go. So that means you're using the experience to build up the P and the R from your observations. And then you already, if you assume those are correct, then you have a tool how to solve this, which is, for example, value iteration, policy iteration, and the methods that we learned. So that's a possibility. However, in practice, that's not really what is used most of the time. Instead, focus in practice is on the so-called model-free learning, where you're not explicitly learning these state transitions and the reward function. Instead, you're basically directly learning how to act and what the consequences are. So again, R and P are not known. You move around, you observe, and you learn on the way. And you learn the state values directly, or better, the Q values, as we see with Q learning and that we look at today. So just to recap, the value of a state is the expected sum of future rewards that may possibly be discounted. In this case, they are not if gamma is 1. In this case, the robot is deterministic. It may not be deterministic. These are, by the way, things that you should really be clear about. So yeah, this could be relevant for the exam. You can expect exercises of the form, what happens if gamma changes, or what happens if the robot is not deterministic. So you have a problem, and then some of these important settings change, and you should be able to use, a simple calculation or even common sense to derive basically an answer. Okay, so these kind of things are relevant. Okay, so yeah, so the value, there's one per state, and the value is associated with optimal actions. Even from this state, you take the optimal action, and then you continue, behaving optimally, as you continue. And the Q values, which you see here, in this case, you have 4 available actions. That means there will be 4 Q values for every state. And the correspondence is clear. So Q value means I fix the action that I take. So in this case, I do the action down, I do the action left, I do the action up, and then from then on, I would behave optimally or following a particular policy. But from this state, there are these 4 actions, and then the correspondence here is that the 7 is this 7. That's the max of the Q values is actually the value. And practically, these Q values were an important contribution to the field that basically gave rise to all these efficient algorithms that are used, because it's really much more convenient to deal with the Q values, because it's trivial than to, for example, extract the action, right? Whereas from the values, we know that that is not as easy. You need to do some effort. For example, there was this policy extraction. So with the Q values, you really it's all clear and there's no additional computation needed. Okay, so this is the and these are the Bellman equations. Okay, Model 3 TD learning. Everybody knows what TD stands for. Okay, let's make a poll. Where is it? I can't make a new poll. Why can't I make a new poll? Never mind. So you can use the chat. You know what TD is? Because I have an old poll hanging there. TD. Yeah, what is TD? Just checking that you have the context. Okay. Yeah, TD stands for temporal difference. Yes, indeed. Thanks, Tejas. The temporal difference learning. And temporal difference is really the key idea that drives these algorithms, and that allows you to make an update after every transition without having to wait for the end of the episode, where you got this, return of the episode. We looked at this algorithm, this type of algorithms previously, that you would run the whole episode and then sort of propagate, make a buffer, and then propagate back what happened. Which is not the best way of solving. And the key idea here is temporal difference, which is that you can it allows you to update your model with every basically move you make. So that's it's called temporal difference learning. And it's mimicking the Bellman updates, but just in one step. So we will see how that works. So this is the standard case of the MDP. So where you have the transition probabilities, the reward functions, and the discounted value of the state where you landed. So you're in state S. You have the choice of making an action, and then you max over those actions that you can make. And there is a weighted average based on the transition probabilities in which state S prime I can end up. There is the reward associated with the transition, and there is the value of the next state. So that's the Bellman optimality equation. This part without the max A, which is this part, is that would be then the Q value. And so the value of a Q state is given here, which can be also rewritten like this, which moves the max operator there. And this is the how you can see it in the tree. So that's kind of the expectimax way of looking at it. And so I'm in this state that has a value associated, I take an action. So that means that would be a Q state, the value associated with that state, but given that I take the action A. And this is the sort of, as you know from the adversarial research, from Minimax, this would be a max node. Okay, I'm the agent, I'm choosing. There's no opponent, so there are no min nodes, but there are chance nodes. Okay, that's why it's this expecting max. And this is a chance node because I commit to do the action A, but I don't know what happens because the world may not be deterministic. So with some probability, I'll end up in S prime, which has a value associated, and it has also a value associated with every action I take from then on. So actions A prime. Okay. So that's and that's all I need. I will not look any further because I have the the values or the Q values for all the states stored. I mean, initially they may be random, but eventually I build them up. And so that's the key idea behind most of these methods. That I don't need to look further. I just make this one step, and there is the estimate of the value in the next state. And there will be a reward that I will be, as I do this transition, I will be getting a reward. So that's the thing that that I would do in the MDP, where everything is available, in particular the transition probabilities. And this is the same thing, but it's for reinforcement learning. So this is gray because it's not available. But instead, I replace this by samples, by trying it out. So that's the key idea. So the core sort of idea remains the same, but in practice, I have to replace this with the samples. So same here, I'm in a state, I do an action, I get to the chance node, and without knowing this, I end up somewhere. So I have to actually execute that physically, basically, right? I cannot just do it like in MDPs, I could just solve it basically using pencil and paper. You gave me the model and I would basically be able to reason. But in this case, I have to actually try it out. I end up somewhere. And then again, from here, I can do different actions, and the values or the Q values I have already stored. So basically that's the model I'm building up, but not the model of the environment, but the model basically just of the Q values. And so this is my trial. So the point is that I do the action A, okay. I'm in the chance node now, and I end up somewhere in ST+1. While doing that, I also get the reward, RT+1. Sorry, I don't have my tablet today. I mean, I have the tablet, but I forgot to take the stylus with me, and that means I'm as if I was without the tablet. And then there is this temporal difference update. So how should I update the Q value and the Q of ST and AT? So it's something that I have stored previously, my sort of current belief. And then it's going to be the difference between the trial and what I was estimating previously. And the trial is the reward plus the discount factor times the maximum over the Q values here. Okay, and so recall you have the Q value stored for everything. Initially they may be random, but you have the Q value stored for every state. So these guys, so I do one actual step in the physical world, I get an actual reward, and then I had an estimate of the Q value in my current state. So that's the Q value of this. So that's the Q ST-AT. Okay. And I should now update it with what actually happened. So I basically can use this one step to compare my expectation, which is this, with the reality, which is the sum of the reward I got for this one step and the expected sum of future rewards, as I would go further down. But I'm not doing that, but I'm just maxing over the Q values of where I could end up. So these are basically the descendants in the tree. Okay, so yeah, take some time to sort of digest it. It's it's this one step look ahead, one step of Expectimax, but you have to do that step in reality, and you get an experience. So there's always this difference in the reward when you make this one step, right? That you have a Q value, a reward that some of future rewards you're expecting, same one level down. The difference between them is this instantaneous reward. And so this allows you to do the update. So you're comparing this, which is this trial, with what you expected, and you're using it to update your estimate here. Okay, that's the idea of temporal difference learning. So, and there is an alpha how you weigh this this update. So if it were 0, you wouldn't do any update. If it was 1, we would update only with this difference. So you would sort of 100% trust what you just experienced. Obviously, the right value depends on things, but you can imagine a sort of small learning rate, for example, 0.1, or you can imagine a learning rate that goes down, over time. That basically reduces the learning rate. So in some of the demos, we, for example, have 0.5, such that it's very visible what is happening, what you just learned from that trial. But in reality, you wouldn't put as much value onto the trial. And I think we discussed this also last time, and in the last Berkeley lecture, it's this exponential moving average idea behind this alpha. Okay. And so it's called off-policy TD control, because we didn't talk about how the action is chosen. We will talk about it a little bit later, but in any case, here there is the max thing, which you see here. And so that means you're considering for your update the maximum of where you can go next. Okay, and in that sense, it's off policy, because no matter what policy you're currently executing, which is even here, you're doing the updates with this max. Okay, so in that sense, it's off policy. Which is different to this other algorithm, which is called SARSA, and that is on policy. Now, what does that mean? The difference here is that rather than taking a max over here, it's taking an AT+1 based on a policy it's following. Okay, so the SARSA comes from, it's basically state, action, reward, state, action. So in Q-learning, you basically stop here. You have ST, AT, RT+1, ST+1, and then you take the max over action. In SARSA, you have this AT+1 there that the policy gives you. So in that sense, it's on policy, because you're updating based on the policy that you're following.
Maybe could you please repeat the SARSA algorithm once more time, because I got a bit lost.
Absolutely. Yeah, it's a bit subtle, but yeah. So the difference is really here, and it's in this AT+1. So if we go back, there is the max over the actions you can take here. So that means in both cases, I have to do that one step. I do have physical action, okay? And then this idea of the temporal difference learning is that, that there is this reward in that step, and then I don't have to, compute any further, but I take the stored Q values for the next states where I land. And the subtle difference is that I use the max of the Q value use next, which is sort of logical, because it's basically, it's optimal, right? And it's the same like what you did in value iteration, that you assumed from then on the agent acts optimally. So yeah, we saw the max operator everywhere, also in the MDPs and in the Bellman equations. So in that sense, it's it's consistent with that. For the SARSA, but yeah, so the policy is not, the policy tells you what to do in that one step. It can be even a random policy. It's going to work. It's just going to work more slowly. And then here, it doesn't matter whatever policy you're following, because you're just maxing over the Q values you have stored in your tables. Here, it's on policy, because here I'm not maxing, but the AT+1 is also given my policy. So select AT+1 is given by a policy. So I'm not maxing, I'm just following the policy I currently have, which in that sense is not optimal. So it's a bit tricky to imagine what is actually happening. And this algorithm has been invented because in some contexts it actually works better. But to sort of imagine this in your head is quite complicated. But it's called SARSA because it adds this AT+1 rather than max over the possible actions from there. Is it more clear now?
Yeah, definitely. Thank you.
Okay, wonderful. So the algorithm is like this. There's nothing really to, we've already covered all of that. This is the key step. This part is the trial. This is this is what we call trial. Oh, okay. This writing with the mouse is a bit complicated. And I think that's there's not much to add. And this is the SARSA. So okay, it's sort of glance back and forth. Here is the max, and here is no max. Here it's the A prime, which is the action given by the policy. Otherwise it should be basically identical. Okay, and then so we focus so far on learning the Q values, and but the other part is that you should take you should choose the action. So how do we do this? So this is the temporal difference update. So we look a bit in that. So you have basically a pool of actions. You can also, that max thing, it allows you to derive it from the Q values. So that's a possibility. Now, so let's say you have two extremes. One is you take always random actions, and you're sure you will explore enough the environment. And the alternative would be something derived from the Q values. So one possibility, you can take always the max, the most promising action, which is the exploitation. So there is this famous exploration trade-off. So let's have a look what effects this can bring. So I could take the max always, but I can run into problems. So imagine we have a maze like this, and so let's say we have two states that bring rewards. I don't know. This maybe bring a reward of, I don't know, 20, and this may bring a reward of, I don't know, 10. So if I always take the best action, so that means I exploit the knowledge I have. So do you see any problems with this approach? What will happen? Right. Yeah. So you're risking of ending up in a local minimum, in something you discover first, which is okay, and and then you exploit and you stay with it. So let's see. I'll share a video using this BBB. Let's see if that works. You see a video running now, I assume.
Yes, we do.
Wonderful. Okay, so this is what we just described. It will always take the max, and so it discovers this goal, which was, let's do it once again. It discovers this goal which was closer. Here you see the Q values, going up, because this gives you a reward of 10, this terminal state. And that's it. So it will converge prematurely in this case. So that's clearly not satisfactory. So instead there has to be some exploration. So I'll show you a version where there is exploration. And you see that it's also, it's much more often ending up in this terminal state, which is positive. But sometimes it manages to go to that other state, which, by the way, has double the reward, which is plus 20. And you see that now already the Q values tell you that this is something better, and that you should really be going for that one. So that's the key idea. Yeah, so I think that's quite clear. And this, this of course takes longer, because there is this random element that for the exploration, but it converges to the global optimum, so to speak. Okay. Yeah, so yeah, exploration versus exploitation, that's the key. Yeah, drive the known road or try a new one, go to the university Mensa or try a nearby restaurant, use the software I know or try a new one, go to business or study a demanding program. Yeah, so our lives are also full of these kind of dilemmas. So how to explore? So one possibility is this epsilon greedy. So with probability epsilon, you act randomly, and otherwise you exploit. That means you use the policy, which could be that max over the available actions. What you know from the current Q values. And just like for the alpha, also for the epsilon, we can think of some schedule how we basically go down with this parameter, such that we make the learning converge. So initially, just like for babies, a lot of exploration is probably good, and as you grow older, you explore less because you already have a lot of knowledge accumulated, and perhaps you also become sort of lazy. But that's that's another perspective. Yeah, problems with randomness keeps us exploring forever. Should we keep? Yeah, that's what we discussed. In addition to this schedule in time, you can also imagine, having the epsilon dependent on where you are in the state space. So, for example, there could be areas which have been less explored so far, and those should get higher motivation to be explored more. So you can imagine the epsilon being bigger there. So what is the actual result of Q-learning? So so it gives you these two things. So it estimates some of the expected future rewards from every state. So those are the actual Q values. And it also gives you the policy. I mean, it's not locked in any table, but it's trivial to extract, because the policy is just you always, in every state, you just take the max. Okay. In areas that have been not explored enough, the policy may be, poorly estimated, and that's why we want to motivate that, that each part of the state space gets explored enough. So, if the values there are really bad, then perhaps there is less motivation to explore, but you just have to explore at least a little bit. Whereas in promising areas, you may want to spend more time there. How to evaluate the learning progress? Right. So you remember there was this trial, and there was the temporal difference update, right? So that was the difference between the. I'm just thinking whether I should try to write it with my mouse. So yeah, I hope you. Or let's go back. Right. So this is the key update, right? So your difference between this and your current estimate, and yeah. So this is how you're updating, and as you can imagine, as soon as these updates become small and smaller and smaller, that means that that's a good indication that your algorithm is converging. So that's an indication that you might want to reduce, for example, the learning parameters, and eventually almost stop learning. Okay, so this is how you can easily monitor the learning progress, that you keep track of these updates, or of the difference of what you estimate and what you get from the current from your current experience. Right. Yeah. So as that goes to 0, then basically it's an indication that you're converging. When to stop learning? Yeah. So in general, the more learning, the better. If you can afford it, it's better to never stop learning. It's better to sort of keep a small learning rate basically forever in those two parameters, alpha and epsilon, which also depends on the, if the environment, or if the problem is stationary, which is that it never changes. Basically, it's fixed. Let's say it's a simulator, it's a grid world, and in that case, you would call it stationary. In theory, you could afford to stop learning, because you can assume that you have already learned the complete thing. In reality, this may not be the case, right? If you have a robot running somewhere, then let's say the weather changes, the lighting conditions change, or there is some fatigue, the motors are hot or whatever, and in that case, that problem would not be stationary. And and when you have still some learning on, this would guarantee that you will be more robust in the end. And so the important topic with which we will end this lecture is going beyond the tables. So generalizing across states. So far we were talking about the V functions and Q functions, and those were represented in tables basically. So in this case, this is the world, but at the same time, this is actually the table with the v values written, or the it could be the q values, of course. So we need a slot in the table for every state, which of course for this world is easy, but for the for if the problem scale, it becomes intractable. By the way, we always visualize these grid worlds like this, that we sort of have an overview. We see the topology, which state is next to which state, but you should imagine that this is not available to the agent, this knowledge, right? So the agent, even if it's in reinforcement learning in general, even if it's model based, it's just learning. It's learning the transition probabilities, but it will never get a map like this, right? It may try to extract it, but it doesn't need to. So it just learns the transition probabilities. If I take the action right from this state 0, I most of the time end up in state 1. So, and that's all that matters for these algorithms. So it never actually makes a map like this, and it never exploits that it's a world with a certain with a certain topology, right? So beyond what is in the exact transition functions, beyond what my immediate neighbors are, I don't have any other knowledge. Okay, so keep that in mind, that we always visualize it like this, but it's not knowledge that is available to the agent. So even if I'm making the model, if I do model-based RL, I stochastically sort of learn what the transitions are, but there is never this step that I would actually draw a map, right? I mean, I could, but it's not happening. And for the model 3, it's not happening at all. I don't even care about where I end up. I just learn the Q values. Okay, so just to keep that in mind, we visualize it like that, but there's no such map in the mind of the agent. So it has just the tables and the Q values. Right. So if the world is bigger and bigger, you will need bigger and bigger tables, which at some point will not be tractable. And so the key idea here is that you should learn an estimate of the value function or of the Q value function from the state. From the state description, let's say, which would be typically some features, something that for the grid world, that might be we can so if you imagine the grid world, what do you think would represent the state such that you can derive the function that approximates the v value or the q value? It's a bit tricky, right? Because the grid world just has these coordinates, but the coordinates are not meaningful, right? Because the fact that something is at coordinate 2 or coordinate 2, 1, it doesn't really carry any information in itself. Unlike when you have the robot, where the state space is actually about the physical state of the robot, whether it's inclined or what is in front of him. So in that sense, in this grid world, you're in a way stuck with the tables, because otherwise, you have nothing about the state. You just have the coordinates, and trying to approximate the value function based on these coordinates is probably not very meaningful. Instead, what you would need would be something like, there is the pit in front of me, or there is the reward in front of me, but that's not part of the state description here. So with the grid worlds, this approximation is not really meaningful, but in the real world, it's indispensable. And so what does this bring us if we do the approximation? It brings us, it solves this space complexity problem for large worlds, because this table simply won't fit in the memory. And so that's one point. And the other point, the important point, is the generalization. So in the UC Berkeley lecture, you saw this Pac-Man example. So, if I'm Pac-Man and I'm here, and then there is the ghost close to me. Okay, sorry about the drawing. Then it's not important that I'm at square, at position 7, 5, and the ghost is at position 7, 6. So if I were to learn in this way, it will take me ages to learn anything, right? Because it would be always specific to my current position and the ghost's position. Instead, what matters is that the ghost is next to me, right? And if I'm able to express in my state description, the ghost is next to me or the ghost is to the right from me, that, and if I will see this once and then I'm eaten by the ghost, then the next time, even if I move to another position on the grid, I will already have that knowledge. So it importantly speeds up the learning because it can generalize, right? So there was this example with the ghost. With the tracked robot, it's the same thing. So what matters is, for example, the type of obstacle in front of you. Is it a stair or is it a pit? It doesn't really matter what the exact shape or the coordinates are, right? So if you are able to map the features of the state onto the value function or the Q value function, it allows you to generalize. So it basically, kills two birds with one stone. Otherwise, it would not be tractable. And importantly, it allows a generalization. So yeah, so here you see it. So in this sense, in this case, the state are the proprioceptive measurements and the exteroceptive measurements. And what you do, you approximate the value function, or in our case, more frequently, the Q value function, as a linear combination of different features of the state or state and action, right? So, for example, one of them could be obstacle, stair in front of me. Action could be, this configuration of the flippers, U shape or V shape, or so. So I'm trying to approximate the Q value. So what can I expect if I see this and this in front of me, and my internal state is this and this, the different features, and the action being, like, let's try with the U-shaped configuration of the flippers. And so that obviously in this world, you would have to make a really, really crude discretization such that you can, use this table-based approach. You would have to basically throw away a lot of the resolution of your sensors such that you can sort of still stick with the tables. So it will not be feasible. Instead, you can basically preserve the continuity, and you can just approximate the Q value function based on the features of the states. W is a weight. Okay, so we're thanks, Rufat. So yeah, so that's something that you need to learn. So yeah, we will see that in the second or in the last block of our lecture after the midterm. For example, we will learn, we will train the perceptron. So this is you've seen also in the Berkeley lecture. This is basically least squares fitting of a function. You're approximating with a linear combination of parameters, and yeah, you're tuning these weights. And how you do it is with this stochastic gradient descent. For you to use any gradient descent, the error function has to be differentiable. So that means you need to be able to do a derivation of that function, and then you can follow that gradient. And yeah, and so you're basically climbing down the gradient. So we will see the details in a little bit. So it works like this. So the new weight is the old weight, and then there is this update based on the derivative, based on, so you have an error, which is, it's again this kind of temporal different step. It's online least squares in this case. So based on this one sample, this one latest experience I got, there was something that I predicted, and then there was something that I experienced. So I basically moved the weights in the direction of of my current sample. So this is basically online least squares. And then I take advantage of the structure that I imposed, which is that there are these independent terms. So I have these partial derivatives of the function with respect to the individual weights. So I basically, it's a weight vector, and I can update each of them separately. And this is the effect they have basically on the error, which is the estimate versus the current sample. Right, and this is called approximate Q-learning, because rather than using those tables, you're approximating the Q value based on the state space description, based on some features. Okay. Yeah, I don't think we have to go into the details, but we will go into them also in the second part of the or the last block of the lecture, when we deal with perception and classifiers and etc. Okay. Yeah, how to design the Q function? Yeah, as you probably know, in all machine learning, there is always this problem of overfitting. So you should not try to fit your data points with too complex functions, such as a polynomial of a high degree, because this will likely not generalize. So instead, you have to do something what is called regularization, that sort of you keep your function with which you fit simple. Which in our case is if it's a linear function, that's that's already the most simple function you can imagine, basically. So with this, I will finish the slides part, and then we can move to the web page and talk a little bit about the midterm. Do you have questions to this? Okay, there are some. I think I don't have to go through this. There are some. Yeah, and this is the book that I will show you in a second. Do you have questions to the slides that we covered today, or to the lecture from UC Berkeley? So, okay, Rufat is typing something. I don't think there will be an assignment for Sarsa, but Philip has a better overview.
Nope, there is none.
Okay. 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 Okay, so I'll share the screen in a second. Okay. Right. So, so this is.
May I ask you, the homework of reinforcement learning is until this Sunday or the next one?
This is, I think, a question for Philip.
Next one.
Okay, thank you.
Okay. Yeah, so then you have time to, this week prepare for the midterm, I guess, and then, yeah. Yeah, so this is a book that is freely available. You can download it from the internet. It's really the Bible of reinforcement learning. And over time, we also adapted the notation basically of our slides that we are more in line with this book. There's a lot of content, so you don't really have to study the whole book unless you're interested. If you are searching for the policy iteration and value iteration, you find it here under dynamic programming. And here is the chapter called temporal difference learning, where you find Q-learning and SARSA. And that's pretty much the essentials that you need. There is an interesting section which is called looking deeper, and that's interesting, at least for me, but depends on your taste. But as we started our course with with the history of cybernetics and everything, where basically the brains and psychology, and it was all under one umbrella, and they were trying to basically look at all these problems of artificial systems and the biological systems with the same lens. Yeah, so this is sort of coming back here, where psychology has a long history of conditioning and basically animals learning from rewards. And recently there's a lot of knowledge also now in neuroscience, how the brain may be doing things like reinforcement learning. So for example, there is a subcortical structure of our brain that is called basal ganglia that has loops with the cortex, and that is presumably, or there is really solid evidence for it now, that it's actually doing reinforcement learning. So just in case you are interested, I think it's a very interesting read, this looking deeper section. Okay. So here is our course webpage. So the midterm will be for 15 points. There is no threshold for passing, unlike in the final exam. And yeah, so yeah, it will happen next week on the lecture. So please attend the lecture. Yeah, maybe we might want to send an email, or Philip also maybe during the labs, if there are people that did not attend the lecture, please tell them that they should attend the lecture for the exam.
Okay.
Okay. Yeah. So yeah, we cover basically topics until now. As I already said multiple times, you can expect something like what you see in the labs during quizzes. So no actual programming, but a little bit of so problem solving on paper. Yeah, all these topics. So you should you should refresh what the search algorithms are. What the differences are between depth first search, breadth first search. What is uniform cost search? Same minimax, alpha beta pruning. You may be asked to prune a simple tree. Yeah, and then MDPs, reinforcement learning. So you have to understand really the context. We may ask you what happens if suddenly the agent is not deterministic anymore, and what will happen to the policy, and you have to be able to solve these problems, simple problems from a computational point of view, but you have to basically understand the important concepts and apply that knowledge. It will be an open book exam, so you can use the slides. You don't have to memorize any formulas. Yeah, but you should not communicate with each other, and we have also like generators of the exam, so there will be a lot of variants of every question or question type. So you will just don't try to talk to one another, because it will only lose time, and of course this is not allowed. Yeah, so that's I think, an overview. Yeah, you have the Berkeley lectures if you want to watch them again. You have also our lectures, which are on this YouTube channel. And you have always the slides and the slides with notes. For today's lecture, I will upload the one with notes. So those are basically those that I use when I'm giving the lecture, where there is additional information about what I'm planning to say. So I believe that there is enough material, and choose the one that suits you best. Do you have questions? Sample midterm. No, really, the quizzes from the labs, this can basically be like a sample midterm. You can expect questions like this, the easier ones, or something that Philip is going through during the labs, like really, like make a simple grid world, make a, do value iteration, or like what will happen if there is suddenly not a gamma of 1 but gamma of 0.7, will the policy change? These kind of questions. Any other questions? No. No. Then I assume that everything is clear. Tejas is writing. Okay. Okay, then. Okay, you too, guys. So yeah, have a good week, and yeah, you see Philip in the afternoon, and then the midterm will come up next week at 10. Okay, so take care and bye-bye.